Hi, my name is Karl Berggren. I'm a faculty member in electrical engineering in the Department of Electrical Engineering and Computer Science at MIT. My research is in the Research Laboratory of Electronics. This seminar is one that I gave as a keynote speaker at the M3 conference a couple years ago in Singapore, and it talks about our work in templated self-assembly. I hope you enjoy it. If you have any questions, you can feel free to email me at Berggren, B-E-R-G-G-R-E-N, at mit.edu. And also you can learn more about our research at our website, quantum.mit.edu. Thanks. So I'm going to talk today about lithography and templated self-assembly. And I've entitled the talk, Lithography and Self-Assembly Below 10 Nanometers, Approaching the Atom from the Top Down. And before I get started, I wanted to tell you that I've actually made the slides available online. So if you have a QR code reader, you can take a photo of that and scan it later. And I'll bring it up again at the end. Or you can just search for my Twitter account, and it's posted there as well. So this is a state-of-the-art ASML stepper as of 2010. And it is the way that nanostructures are made by industry. It is, you can see, quite large, quite sophisticated, and it can produce more than 100 wafers, 100, 300 millimeter wafers an hour with features down at the 40 nanometer length scale with exquisite precision and alignment layer to layer. But this is not really relevant to the current discussion. Much more relevant is this type of lithography. Lithography based on beams. In particular, this example of electron beam, you start with just a beam of electrons, some apparatus for focusing it, and resist, and then you have a means of deflecting the electrons across the resist and means of translating the substrate from field to field in order to stitch together full area patterns. So let me ask a question in the audience at this point. First of all, how many people have heard someone say, well, electron beam lithography is slow? Okay, wow, okay, there you go. Well, it's okay, admit it, yeah, okay, more than half the people there heard that said. So, and I would contest that. And I would say the difference between electron beam lithography and, say, optical lithography or other optical methods is really a question of what problem you're trying to solve. If you're trying to get, say, 50 people from the Park Hotel to the conference center, the fastest way to do that is to use a bus. It's simple, it's convenient, it gets you everyone there in time. But if you want to get one person there, the fastest way is to use a sports car. So electron beam lithography is the sports car lithography of patterning. Because what it can do is take a pattern from an idea that's in a computer and transfer it into a real material system. And it does that at incredible rates. So we heard from the speaker this morning, 40 codons per second decoding rates for biological systems. Electron beam lithography can process information and put it into a substrate at data rates of 10 to the 8 bits per second. So it's many, many orders of magnitude faster than biological systems for that. And it's the only real way we have to quickly get information into a substrate. So if this tool is not useful for mass manufacture of integrated circuits, what is it useful for? Well, first of all, for the kinds of things that we're all interested in doing in this group, for manipulating matter at the sub-10 nanometer length scale, for doing research, and for developing prototypes. But furthermore, for manufacturing of high-value, low-volume items. So, for instance, amplifiers in your cell phones. You know, the gates on those amplifiers can be patterned by electron beam lithography very efficiently and at low cost because it's not a highly integrated system. For another example, magnetic recording heads. You need a very small feature, but each disk drive only uses one, and it takes an electron beam just a fraction of a second to pattern such a system. So the work that enabled this, the ability to grayscale pattern at the 100 nanometer length scale, actually derived out of Joel's thesis work with me, in which he demonstrated 4.5 nanometer length scale features in hydrogen silsesquioxane resist, which is a silicon-containing resist, and it's going to come out through most of our work that we're using this hydrogen silsesquioxane resist. And what was developed was this high contrast pattern that allowed us to realize dense hydrogen silsesquioxane patterns at the sub 10 nanometer length scale. You can see here what's challenging about a pattern like this, even for electron beam lithography, is that you need to be able to expose this region and this region only 9 nanometers apart without inadvertently exposing the region in between. All right. So I'm not going to focus on electron beam lithography because electron beam lithography at this point is a more mature field. So I'm going to focus on some of the new emerging methods of beam-based lithography that may apply to this. So one of them is lithography with helium ions. This was one of the very first patterns we made with helium ions. So helium ions can expose resist just like electrons can expose resist, just because they decelerate as they enter the resist, and as they decelerate, they deposit energy which breaks chemical bonds in the substrate and the resist, and that affects chemical change which you can develop. This was an attempt to write this pattern here, just with straight lines through it, a wagon wheel pattern. And because this was one of the very first helium ion microscope tools that had been developed by Zeiss, actually by a small company named Alice that Zeiss eventually acquired, the tool had a lot of vibration. And so as you wrote, the beam sort of wiggled all over the place. And this would have been disappointing to some, but we were actually very excited to see this, because if you looked in at the smallest length scale, there's a little bit of vibration here from imaging, but you could clearly see that this new agent of lithography had resolution down below 10 nanometers. So at least as good as electrons. So we wanted to understand, is it as good, is it better, or what are the differences between exposing with helium ions versus exposing with electrons? Now, one thing to understand, this tool was built to be a microscope. So it is basically a very small spot size, about a 1/4 nanometer spot size, that's rastered across the substrate. And then we just adapted it to lithography by putting a pattern generator on it. And what you see is really nice resolution at the 20 nanometer pitch, or 10 nanometer half period patterns. So you can look here, this is a secondary electron cross section, it goes back and forth. It's basically fully modulated. Here's the background, here's the baseline, and you can see quite good modulation. Now down at 5 nanometer half pitch, it's not quite as good. And I think you have to kind of, it's not fair at this point to compare these tools to the electron beam tools because, of course, the electron beam tools are so much more mature. So the difference in resolution here could just be a little bit of residue vibration or something like that. We don't really understand at this point what limits it. But one thing I will say is that unlike electron beams, when a helium ion enters a substrate, it scatters very little. So an electron will enter a substrate, move around in the substrate, and eventually come back out. And when it does that, it exposes a region on the order of micrometers around the central spot with a very, very low, what's called proximity dose. When you do that with helium ions, there is a little bit of scattering on the order of a couple hundred nanometers, but the dose is so small that there's basically no appreciable effect on the pattern. And this is a fully proximity affected pattern. This is a few hundred nanometers by a few hundred nanometers. So a helium ion entering the middle here would expand on that order around the middle, maybe a couple hundred nanometers around the middle. And in the corner here, we have a much lower density. The dose for electrons would be substantially lower than at the center. But you can see if you look in very closely, the dots are basically the same diameter at the center as they are at the edge, even on this very small length scale. So this is one of the key advantages of helium ion beam lithography. The high resolution that at least matches the resolution of electron beam, but also this absence of the proximity effect. A more subtle point, which I didn't really have time to discuss, is that when the helium ion enters the substrate, it slows much more efficiently than an electron slows. And as a result, it exposes the resist much more efficiently than an electron would expose the resist. That leads to less heating in the substrate, which is a big issue in direct patterning of devices. And also it would lead to, if you could make a beam with the same current as an electron beam, it would lead to faster writing times than electrons. So after Zeiss developed this helium-ion microscope, they adapted it for use with neon. So they were interested in this, in part I think because neon has more mass than helium, and therefore it would be efficient at milling materials. So it would be a way to do nanoscale milling without some of the disadvantages that are associated with gallium. Of course, we looked at this neon opportunity as a way to study the high-resolution beam-based lithography, and saw immediately in our first work length scales down around 7 nanometers. So length scales that are close to the resolutions we've achieved with electrons or helium. Sorry, it's a 7 nanometer half period, a 14 nanometer period for a dense structure. We also see similarly minimal or non-existent proximity effect in this system. Because the length scales are so small, we're better off imaging these with transmission electron micrographs. We see a slightly rougher edge than we're accustomed to seeing in similar electron beam images. And we ascribe that to the fact that the sensitivity of the resist at this length, to this material is 1 ion per square nanometer. So one of the ways to think about this is when a neon ion at 20 kilovolts comes into a resist, it loses energy at a rate on the order of 1 keV per nanometer. Okay? So think about it in terms of chemical bonds. A chemical bond might be on the order of 2 eV. So it's breaking 500 chemical bonds per nanometer. So it's a very intense radiation dose. Essentially, 1 ion moving through the resist exposes a region, or is expected to expose a region right around it. So that's a different regime than we're used to. We published this work just this year in Nano Letters. And it has some interesting possible consequences. I don't know if I did that, but it was cool. So I'm going backwards. It'll be a very long talk about it. Okay, so what are some of the things? So one of the things is that neon should push lithography well into the shot noise regime. So you might say, well, that's exactly what you don't want, right? So ions are being produced randomly at the tip, and so shot noise is just that in a given, say, nanosecond of time, how many ions are emitted varies due to Poisson processing, and therefore the dose will vary. And this means that we would see this shot noise in the resist exposure. That would sound bad, but of course, because I'm interested in studying lithography, that's great, because that's really hard to see in electrons, so we'd like to understand that regime. But the second result of that is in 2003, not a heavily noticed work, but I think extremely interesting, is this work out of Darmstadt, where they showed that they were able to actually sense single ions during exposure of a substrate. And that means that you could, in principle at least, think about detecting the single neon ion. When that 1 kilovolt of energy is lost in that first nanometer, emits a lot of secondary electrons. You could detect that pulse of secondary electrons conceivably, and you could then gate back to your blanker to basically regulate your dose at the single ion level. So you could potentially suppress shot noise in the system with the correctly built system. So that's a very interesting possible goal. Another thing is people worry that neon might result in sputtering, but we've observed that it doesn't, just because it's so efficient at exposing resist, more efficient than it is at sputtering. Okay, so before I go on, I want to mention one more thing about metrology, and it relates to the next part of my talk. So I'm going to talk now about how this can be integrated with self-assembling systems. If you look here, this is a top-down view of a post that was fabricated by one of my students, Huigao Duan, who's also now here at A-Star, actually, and is probably out there somewhere in the audience. There he is. This was a HSQ pillar, so you have to imagine it, and you're looking at the top, and it just looks like a circle, right? You're looking down a cylinder, and it's a very tall pillar, and when it collapses, you can look at it in a transmission electron micrograph, and you can see exactly the exposure down the pillar. And you can see it's a 3 or 4 nanometer length scale. And this is quite useful for us in metrology. When we try to do metrology on these SEM structures, we're severely limited by the electron microscope. So using transmission in electron microscopy provides you a much more detailed picture of what's going on in these systems. So why is this relevant? Because, well, this process of nano-collapse, actually, if you look closely at these images, you can see it here too. This was a fence-like structure, like a long fence that collapsed at the edge, and so it's twisted here, and similarly here. And this allows us actually to do better metrology on it, and it's been the bane of the existence of the sub-10 nanometer community for a long time, actually. So when you try to, I would say sub-100 nanometer, when you try to make high aspect ratio structures in resist, they just start falling over. Okay. So a lot of effort has gone into trying to avoid this problem. And Huigao's remarkable insight here was that, well, if you can't beat them, you should try to join them. So could we use actual collapse to improve on bead-based lithography? And this is one of the early images that convinced us that there was some element of control that we could use to engineer this. And this was an area of posts, so these would have just been a large number of dots, exposed with HSQ and then developed using a liquid developer. And when you develop them, when the drop dried off of this area, the posts all collapsed. But they collapsed in this sort of rather non-random way that was curious. They seemed towards the edge, they seemed to all collapse inwards. So something funny was going on here. So if we look at this type of a structure with partial collapse, with highly sparse dots, the collapse is more random. So it seems like there's sort of forces between the dots, perhaps acting here. And so the experiment that Huigao tried was to take a cylinder and to only pattern half of it. Now, this is no mean feat. When you're at a 15 nanometer diameter cylinder, you're trying now to make a 7.5 nanometer asymmetric structure. So it's but Huigao was able to find a way to approximate that type of structure. And when he did that, he found that the posts all fell down the same way. And that direction was actually not, I just blinked it, sorry. That direction was not set by any kind of fluid motion or spinning or anything else that was happening in the substrate. It happened only due to the way he structured it. So for instance, if he structured them pointing horizontally, they all fell horizontally. If he structured them up at 30 degrees, or at 60 degrees, or up at 90 degrees, they correspondingly would point at 30 degrees, 60 degrees, or 90 degrees. Published this year in Small. Furthermore, it could be individually controlled locally. So you could have here, these structures would collapse inwards, these ones collapse outwards, these ones collapse inwards, just because the pattern was shaped like this. Similarly, you can make chevron structures, these kind of square-like structures, hexagons that alternately collapse in or out, depending on how the pillars were oriented. Now, why would this be useful for electron beam lithography? Well, first of all, it's just interesting. So nano-collapse is something that people have studied for a long time as a disadvantage. Now, if you can engineer it, you could start to think about what is it that controls it and maybe get at a better sense of how to eliminate it in systems where it's not desired. But also, when you expose electron beam resist, the electron moves through the vertical part of the resist for free as it slows down. So you expose a large region of resist material vertically. If you then engineer that collapse and turn it into a linear structure, you've basically gotten away with what would have been a series of exposures and done it with a single point. Therefore, you've got a much faster exposure process at the expense of thinner resist. So it's a trade-off, but at least it's one more knob that you have to turn. And this is a big deal in terms of cost. In electron beam lithography, currently, you can easily spend $1 million making a mask for a state-of-the-art optical lithography process. And you typically have to make on the order of 30 of these for a run or more now. So being able to, say, reduce the amount of lithography by even 50% by having some of the structures patterned by collapse could be an enormous cost savings to the industry. This could also be done, this was work done in collaboration with IMRI now, this could also be done by taking a fence-like structure, so a little line, a patterned line, and by curving the line, you can induce the whole line to collapse in the direction. And made this square-like pattern here. Also made the MIT logo. So the MIT logo is it's a bit of a cheat, because it's almost like the graphics designers who made this logo consulted with me first and said, what would be a really easy pattern to make lithographically? And so they made it like these blocks that are all lined up and little squares with nice rectilinear Manhattan geometry. Perfect. So we thought, well, let's pick a harder one. So we picked the Imri logo here. So here you've got like 45-degree lines and so forth, and he could make those too. So this is quite a nice little method. Related to this method is capillary force-induced cohesion. So when two structures, so these are all sparsely spaced structures. When two structures are close to each other, they collapse into each other. And indeed, there's been a great deal of work studying this. So this is drying with critical point drying, and this is drying with a liquid drying. And the liquid drying induces cohesive forces due to capillary action that causes the posts to glue together during drying. And one of the pioneers in this was actually Joanna Eisenberg, who was going to give the other keynote, but wasn't able to because she was ill. So, and this has been since 2003. People have been looking at this type of capillary action during drying. This is an example from this paper, Lau et al. From 2003, but also a number of other people have worked in this area. So what Quigal's work focused on was actually taking pairs of structures and triplets and quadruplets in various arrangements. And by creating subgroups, groups of posts that were spaced closer together than the overall period, is able to engineer exactly which posts the different subgroups would collapse into. So it's able to make these beautiful structures with this method, which could be interesting for things like metamaterials or nanoscale plasmonic devices where you might want to create those structures. But at this point is perhaps most interesting just as another technique in the toolkit. Because we've got exquisite control of positioning in lithography, we can actually create hierarchical collapse, where by positioning some subgroups more closely together than other subgroups, we can order the collapse so that the collapse first occurs in from the edges and then from the center, and you end up with these structures which we call chicken feet structures because they look like chicken's feet. And then you can do it with 4 elements and 6 elements, and you can actually do multi-layer nano chicken feet structures with this. So this starts to look like the kind of pattern that you would need to route signals on a substrate. Okay, so those are methods of physical self-assembly based on beam-based sub-10 nanometer lithography. I'm going to move on to chemical methods of self-assembly. And before I talk about it, I'm going to give a kind of overall vision for what I think lithography is going to do in the next 20 years. So right now, the way we do lithography is we basically, for the formation of the patterns for the masks, we basically come over, and the pattern we want to write, pixel by pixel, we address it with an electron beam. So if we have a big square, we still go in there and we pattern the whole square. Electrons hit every single element to be patterned there. And the analogy I'd like to draw is the one where you're trying to build a fence, say, with your neighbor. And if you're smart, you don't want to have a fight with your neighbor, you get a surveyor first to come in and tell you where the boundary line is between you and your neighbor. And they come and they charge you, $200 an hour or something to do that work. You don't say, while you're in the neighborhood, would you mind building the fence and painting it for me? Because you're paying that person way too much to do that kind of work. But right now, that's actually exactly what we do with lithography. We come in with the electron beam. This electron beam has an incredible mechanical alignment system in it to allow us to position structures very, very precisely. And we use that same structure to then basically just fill in the patterns, that same expensive tool to fill in the patterns. But these modern methods of chemistry of self-assembly are emerging that should allow us to let the lithography tool do what it's best at and input information into the substrate, and then connect the dots and fill in the intermediate structures using only chemistry. And so these would be the low-paid work crew that comes in and basically just builds the fence and paints it and then heads off. So that's the idea. One very simple chemical system is the block copolymer. The block copolymer can be thought of, this is a review article on it if you're not, if you don't know about them. By the way, the link that I showed at the start and I'll show again at the end has all the references from the paper, so you'll be able to get them all there. But basically, the way I think about this chemical system is these are two polymer systems that have different enough polarities so they want to phase separate, right? So they want to become oil and vinegar in a solution. They want to just get away from each other. But you covalently bond them together. So they can't. So they can only microscale phase separate. So locally, on the length scale of the polymer's lengths, they can phase separate. But then they can't get further apart than basically the handcuffs that are holding them together. Okay? So these are a well-studied system in material science. And they form all kinds of interesting microphase patterns on the 10 nanometer length scale. So this is a spherical type pattern, this is the cross section, this is the top view, and in our case we use a polydimethylsiloxane, which is a silicon containing polymer for these structures. And I should mention this work was done in very close collaboration with Caroline Ross's group at MIT, and a number of other groups over the years. Two of the phases, these systems form many phases, two of the phases we're most interested in are the spherical phase and the cylindrical phase. The spherical phase is exactly what it sounds like. It's little spheres of silica containing polymer. The cylindrical phase, little cylinders that lie in the plane and make sort of meandering type structures like you show here, this fingerprint type pattern. And these patterns are both characterized by excellent local order. So if you look at this post, it has exactly 6 spheres around it, but not very good long-range order. So there's many sort of grain boundaries and defects along here. So what happens if you lithographically can make a structure so small that it can actually fit inside of one of the microphases is that you can actually cure that problem of long-range disorder. And you can do it basically in a way that's completely invisible to the blockable polymer. This domain and this domain have no idea that this domain is not a real domain. It's basically a surrogate that looks chemically to them as if it was a real microdomain. And as a result, you can basically position a few of these sort of programmed cells where you want them, and then the rest of the structure self-assembles around it. So this is the untemplated pattern, and when you insert the lithography, this is what you get. This was work by Joel Yang when he was in my group, and you can see here, essentially the posts are so small they just disappear inside these 15 nanometer diameter pillars. In fact, you can hardly even see it if you look closely. There's also similar work, by the way, by a number of other groups, Neely, Russell, Kramer, Joy Chang. But in our case, you can see we got about 9 pillars, 9 spheres templated for every one post. I'm going to skip over this in the interest of time, but there's a lot of work also in other types of templates for blockable polymers by other groups. So when you take these same periodic pillar structures and you template it with now linear patterns, you end up with a ability to template the angle of orientation. And so here, the angle can be controlled simply, whoa, am I being cut off because I went too long? Okay, no, all right. I think I was just cutting it, oops, turning it the wrong way. So the pillars can basically, by the period here, you can adjust the angle of self-assembly. So we can actually program in that angle. And we can also scale, this is work by Jae-Byung Chang, who's got a poster on this subject at this conference. And we can actually scale this down to the sub-20 nanometer period, 10 nanometer half period. And this is showing that we're able to adjust the angle by adjusting the post period. There are some complications. So for instance, it's very hard to realize multiple morphologies on the same substrate. So you can either have spheres or you can have lines. So we're now working on that. You're limited in the natural period to about 30 or 40 nanometers unless you scale to a smaller blockable polymer, which is what Jae-Byung's work has focused on. And then you'd like to more complex, more arbitrary structures. And one of the last things that Joel Yang did in my group just before he left was to show that basically by templating instead of with dots, with dashes, you can locally control these structures. So you can actually create regions that are templated, so the bright white is the template and the gray is the self-assembly. You can create regions that go back and forth exactly where you want them to. And it's basically by creating a lattice where the templating is degenerate between two possible orientations, and then just using that local stress to break that degeneracy. In the work by Jung-Gon Son, out of our collaborator Caroline Ross's group, he was able to basically pattern using 2 different solvent annealing methods. So normally we thermally anneal to form the self-assembly. In this case, he solvent annealed, and as a result, we got some regions with cylinders and some regions with spheres depending on the solvent. After electron beam irradiation, it actually fixed that local region to whatever the phase was initially. They went back into the solvent anneal and changed solvents. They're actually able to reverse the phase. So they're able to mix different phases, posts and lines. So this is regions templated with posts. This is regions templated linearly. So I think with that, I'll finish up. Hopefully I left enough time for questions for people. I just wanted to acknowledge all the people who worked on this area. A lot of people have contributed, as well as to thank my sponsors very much for their support over the years. That's the reference that's available online, and that again is the QR code if you want to get access to the online version of the talk.